In this lecture, we'll talk about the non-silicate minerals, and I'll delve a little bit into the particular classes, although we're really just scratching the surface with this. Here are our mineral classes again, and we're going to save the silicates for later. So this is just about non-silicates here. The simplest of mineral classes is the native elements. So these are elements that consist of a single element, like gold, silver sometimes, copper again sometimes, and we can even find iron in a pure form. There are some nonmetals that do this with sulfur, diamond, and graphite. A couple of important things that I want to demonstrate using these native minerals because it's fairly simple to see, and we're going to need the ideas of it when we get over into the silicates, which are much more complicated. So this idea of solid solution. Okay, so let's think about a native metal like gold. So it's composed of gold atoms, metallically bonded together. All right, consider the idea. Let's look at these red atoms here as if they're gold. All right, each of these is an atom of gold, metallically bonded to its neighbor in one of these lattice structures. We need the lattice to make it a mineral. So consider the idea that silver is similar enough to the gold atoms that a silver atom could sneak in amongst all the gold atoms. And that would be okay with the lattice. The lattice wouldn't be too strained by that. It could handle that. And another silver atom could sneak in, and another, and in fact, you could have a complete continuous is important here, series all the way from all gold through half and half, all silver, and every ratio in between. And the every ratio in between makes it continuous, and it gives us this idea of a solid solution series. So digest that now while we have a simple system of just gold atoms and silver atoms, because that's going to be needed when we get to the silicates and we have a little more complicated structure to redigest that idea with. And here we're going to see that solid solution idea in practice. And phase diagram again, and you're used to seeing phase diagrams. Now, this one's set up a little bit differently. We don't have a pressure axis. We have temperature, vertical, and then on the horizontal axis, we have percentage of gold. So all the way over here at 100%, our phase would be what you would see as red gold. And then a little less, and you get a yellow. And then you get these greenish yellow and yellowish green versions. And then all the way over here to almost all silver with just a little bit of gold in it is your white gold, or whitish gold. And then I would also point out that you have another physical property other than color going on. And don't worry about the fact that this is split. That'd be an upper level course thing where you talk about partial liquidus. So don't worry about that. Just look at the idea of the overall shape of it, that the more pure gold version, and remember this can have every percentage in between, but the higher percentage gold correlates to a higher melting temperature than the lower percentage gold, which in this case would be higher percentage silver, has a lower melting temperature. And it's continuous. Again, you can have everything in between here along this line. And we've talked about the more typical phase transitions before, like in the graphite diamond system. Both of these minerals are composed entirely of carbon. So if you could break it down to the atomic level, every atom is carbon, right? But wait, graphite and diamond are different, aren't they? Well, of course, and we use a phase diagram. There's a phase difference between diamond and carbon. And you see it here that diamond is stable under much higher pressure. These are billions of pascals, gigapascals, than graphite, which is stable under more normal pressures and into the deeper pressures, but not all the way. I also point out that we have liquid over here in a couple of different phases. So you have your multiple phases of liquids. So is your diamond ring, is it likely to just suddenly change to graphite? The answer is no, because we have a thing called metastable states. But you really don't want to heat that diamond up or shock it or anything like that, because you can destabilize it. It's not a true stable state. It's metastable. And if you give it just enough energy to get over an activation barrier, it will revert to graphite. Our next mineral class is the sulfides, and you've seen at least one of these. Um, I think we saw galena and pyrite in lab. Sphalerite we talked about with the multiple cleavages, and down here you see an example of the two of sphalerite and galena growing together. Here's your big galena crystals, and then your sphalerite crystals going on top of it. And here's an example of pyrite crystals. And pyrite also has another aspect that we can talk about, and that is the idea of sulfides and acid mine drainage. Here's a chemical equation showing the weathering of, here's your pyrite, right? And this is oxidative weathering, so the oxygen is attacking this mineral along with water, hydrolysis, and you get free iron ions, and you get the sulfates. And this sulfate with the two H pluses, that's equivalent to sulfuric acid in solution. And you can get so much of it. Here's and it's in the references here. Here's a sample being collected in an acid mine drainage situation in Colorado, and they're measuring a negative pH. And a lot of folks don't even know that a negative pH can happen, but it certainly can. I have actually measured a negative. It wasn't quite this low. It was negative 0.3, but I've actually measured it in a pond on the surface over in Graves Mountain, Georgia. The pond looked like this blood red color right up here, and it was seriously dangerous acid mine drainage. Our next class of minerals is the oxides. And oxides are super important ore minerals. And what I mean by ore minerals is this is where we get a lot of our metals and other materials from ores in the ground. So hematite, magnetite are iron ores. And if you know anything about the mining history in Birmingham or over here on Pigeon Mountain and Taylor's Ridge, the iron that was mined there was mostly hematite ore and sometimes limonite. You could have another ore called rutile. This is where we get titanium. Corundum doesn't make very much of an ore because this is such an incredibly hard mineral. Diamond is 10, it's the hardest, but corundum is next at 9. So it's really, really difficult to process. Cuprite and uranite, they make really good ores for copper in the case of cuprite, or for uranium. There's actually uranium ores, although it's not exactly uraninite, it's a uranium sulfide, but there are uranium ores in the Chattanooga Shale, one of the units we'll talk about in the sedimentary unit, right around in this area. So these guys are important as ore minerals so that we can get some of the materials that we need from the earth. Now, let's look specifically at the iron oxide minerals. So iron is Fe. It's atomic number 26. And if you look back to that periodic table, you'll see that it's in that area that I talked about, does weird stuff with the oxidation states. It's kind of in that transition metals area. And iron can have multiple different kinds of oxidation states. So commonly it has oxidation states like +2. And we'll see that in the wustite mineral, so that this iron has a +2 on it, and oxygen, remember, is in that column where you can guarantee that it's going to have a -2. So a +2 and a -2, one of each, and it balances out. But it's not as simple as that with iron, because iron can also have a +3 oxidation state, like in hematite. Okay, well, let's see. We've got 3 oxygens here. They're -2 each, so 3 times -2 is -6, right? We would need a +6 to balance that. So 2 iron with a 3+ on each of those will do. So iron can lose 2 electrons in the case of woostite and be an iron 2+, or I could lose 3 electrons in the case of hematite and be a +3. In fact, magnetite is a special case because it's got both a +2 version and a couple of +3 versions in it. And that's actually what gives rise to the magnetism, is because of those unbalanced iron oxidation states in the mineral. So you've got a couple of these irons are +3s and the other one is +2. So you still have your 8 negatives and you have to have 8 positives to balance that out. In fact, we could take this a step further and write these iron as if they are different elements within the framework of that mineral. We could write it this way, that we've got 2 of these guys, iron 3+, and 1 of these guys in this parentheses with iron 2+, and we still have our 4 oxide anions. We can have halide minerals, and halides are minerals containing the halogens, which is that column 7 over there that likes to grab somebody else's electron, just one, like chlorine did with sodium. So you can have chlorides and you can have fluorides. We've seen all 3 of these minerals in the lab, although I didn't point out the sylvite. It's actually in one of the halite samples as kind of the orangey veins inside the halite, and basically it's just a potassium chloride instead of a sodium chloride. Carbonate minerals. Carbonates are a particular favorite of mine because this is what a lot of my caves and cave formations are made of. It's calcite right here. Notice that both the calcite and the aragonite arrows are both pointing to the same formula, CaCO3. And if you guessed it, that is another one of those situations where we have a polymorph. We have 2 different phases of the same formula, 2 different minerals that are exactly the same chemical formula. They exist under different temperature and pressure conditions, and maybe some other more complicated conditions with aragonite as well. And then dolomite is similar. Dolomite is also found in a lot of the rocks around here, where half of the calciums are replaced by a magnesium. So you have a calcium carbonate, magnesium carbonate. So basically 2 carbonates on it. The nitrates class, we can have a couple of different options here. I know that, well, we'll talk about the borax in a second. It doesn't actually have any nitrate in it, but it still counts as nitrate class. All right, so saltpeter does, KNO3, and if you've ever looked at gunpowder formulas or how we used to make gunpowder, the old black powder used a lot of saltpeter in it. I think that they have gotten, I think this was replaced with an organic compound at this point, but this was the original. So so potassium salted with NO3, which is a polyatomic anion with a -1 charge on it, nitrate. So that makes a nitrate. Well, of similar structure, but much more complex, are the borates. And so you have boron, that strange atomic number 5 element. And it does some strange things in organic chemistry if you ever take that too. But anyway, you have a salt system just like you did up here. And then you have some hydroxides on that. And I want to talk about this last part of the mineral because we're going to see this occasionally in mineral formulas. Okay, so you're familiar with H2O, and that is the water molecule that you're familiar with. But this dot included in the formula, what it means is that these H2Os are intact, 2 hydrogens and an oxygen stuck together, and as a unit, they're interacting along the structure of the rest of the mineral. And I'm going to talk about that in a little bit with the sulfates. I just wanted you to see it early, that you can have this dot and include some number. It's not always 8. Sometimes it's 6, sometimes it's 4, etc. But including 8 water molecules as integral parts of the crystal structure. So I mentioned barite when we were talking through in the lab stuff because it's so dense. And then here's we saw, well, actually we saw this one, gypsum, in the lab. There's another version of calcium sulfate called anhydrite, which we did not see. It's a much harder mineral. Remember that gypsum is really soft. It's the one that would scratch with a fingernail very easily. Other than that, it looks like the cleavage pattern looks like calcite, but it's just so much softer than calcite, and it does not react with acid either. But this version, anhydrite, is much harder. Off the top of my head, I want to say it's about 4.5 or 5, so actually harder than calcite. Now be careful with this. This is not a case of just a phase transition because these two water molecules in the structure, they are integral to the gypsum structure. They're actually integrated into the crystal pattern. So this change is actually called a dehydration reaction. So it's actually a chemical reaction, and we no longer have the same chemistry. So we have to say that that's not just a phase change, it's actually a different mineral system because of the water. So that does it for our non-silicate minerals. And next video will be our silicates and all these different classes of silicates. Now, remember that you need to do that silica tetrahedron assignment so that you build those tetrahedrons, take a picture of them, upload it so I can see you've got them in hand, so that we're talking about those as we build through these, because that silicon tetrahedron is so important in how these silicates work. So I want you to have a manipulative so that we can talk through it. See you next time in silicates.